We are forging ahead at Allen High School, talking about the structure of an atom, atomic theory and structure. Now, we were in the midst of discussing spectra and the atomic emission spectra that we'll see. You should have watched the video on that I was hoping would make it even a little bit more alive for you. Now, I want us to actually start some calculations. Now, when we use that equation that I gave you, that the energy for a particular energy level is minus 2.178 times 10 to the minus 18th z squared over n squared. That's what we're going to be using right now. I'm going to do one or maybe two of them for you, and then I want you to do the rest. Again, those calculations will be part of your notes grade that I will be checking. So I want you to do those calculations. I'll get us started at least, and then I put in a graph that I think will make it a little more visual. Now, when we use this on other substances, we're really just getting an estimate. For one, we're going to look at this little guy here soon, and we're going to find out that it's not quite exactly equal to the number of protons in the nucleus. So that's only one of the issues. But it's going to give us, I think, a good indicator of some of the differences between the elements. So let's go ahead with lithium and calculate that. I have minus 2.178 times 10 to the minus 18th. And lithium is element 3, so that's going to be times 9 squared, 3 squared. And then we're going to be doing energy level 1, well, that's over 1 squared, right? So that would be over your 1 squared. And if we did that, we're going to get a value for this little block here, that's the calculation I'm doing for you, of minus 1.96 times 10 to the minus 17th joules. So this is pretty much plugging and chugging. Now, I don't have it fully calculated for you. We'll see it in the graph. But if n was equal to 2, the only difference would be, if we were dealing with n equal 2, is that we'd have 2 squared or 4 right here. So we've increased the denominator. So that means we're going to decrease this value, or in this sense, it's actually going to make it less negative. Right? So it's shooting towards 0. In effect, that's when the electron's gone. There's a continuum, the electron's been ionized. So you need to be able to plug and chug into this formula. I'll be honest with you, the likelihood of you seeing something other than hydrogen on an AP test are slim. But I think evaluating it as an estimate to try to understand some of the issues of structure and function and difference in spectra will be very valuable for us. So make sure that you have all of these plugged in. And especially, I want you to start looking at these and evaluating which one will have the largest energy difference between the two, and hence which would give off the longest wavelength. Well, actually that would be the opposite, right? Because as you increase the energy, we're looking at decreasing the wavelength. So largest energy and then the one with the longest wavelength. Now, I think the next chart will help you with this. I made this graph. I had a little bit of trouble with it when I was working with, going between my Macintosh and my Word, but this gives us a good indication of what we're doing. This is lithium, and this is boron. That's from the chart. Whoops, this one there. This is nitrogen, and this is fluorine. Now remember, we're representing the nucleus down here somewhere below these. So that means that this blue is n equals 1. I hope I'm still on the movie. And this red is n equals 2. So I'll put it over here just in case that went off the screen. Now, what I want you to notice is that the quantum number energies are not the same for different substances. Lithium's is way up here, whereas fluorine's is down here. That means that the closest electron in lithium is further away from the nucleus than the closest electron in fluorine. Now, I hope that makes sense, because lithium has a +3 charge. Fluorine has a +9 charge. That negative electron really wants to get close to that +9 charge. That's going to be leading us into some of the justification that we need when we ultimately get into periodic trends. So very, very important. As we increased our nuclear charge, we are going to decrease the energy for each level. As you see, 2 is also a little bit lower. And that means it's closer to the nucleus. And that's going to have an implication on size, because the closer the electrons are to the nucleus, the smaller it will be. We'll revisit the smaller part later. Now, there's something else that I want to show you on this. And, oh, darn it. Control Z, my favorite friend there. I got rid of my diagram too when I did that. Let me just erase. Now, I want to show you something else on here. If we're going to look at atomic emission, remember emission is going from high N to low N to a low energy level, right? And that gives us delta E. Now, delta E in an emission is negative. Well, we're looking at a wavelength of light coming off, and wavelength can't be negative. The delta E is negative. You have to keep the negative sign there. But when we look at the energy of the photon, that we take the absolute value of that difference in energy. That's going to be the energy of the photon released. Now, you notice that that difference in energy is smaller for lithium than it is for fluorine. A much bigger difference. The key here is that the N equals 2 to N equals 1 transition has a different delta E for each, and hence you're going to see a different wavelength of light. And that's why each element has its own unique atomic spectrum. So we can use it as a fingerprint to identify that substance. So just because it's N equals 1 doesn't mean it's an exact energy value that is the same all along. That's the point I was trying to make there. So let's then go into one more problem on this. Hopefully that helped. If not, I can certainly reteach it in class. Next is the calculation of the energy involved, and then we're going to calculate the wavelength of the light observed for a transition, an emission, or absorption, haven't specified yet, for hydrogen. Now, first off, I hope you can see it's going from high to low, or another way to think of it is N final minus N initial, okay, is going to be a negative number, or N final is, less than N initial. Almost said that backwards, sorry about that. N final is less than N initial. So hopefully you've got a guess in your mind right now, but we're going to go ahead and do this calculation and then move on to the second quantum number. So the energy for energy level 5 would be minus 2.178 times 10 to the minus 18. The energy, or Z for hydrogen, is simply 1, so it's usually completely left off even the formula. So 1 squared is 1. We don't have to worry about it. And this would be over 5 squared, which is 25. And you would solve for that. Your book gives you a combined formula that will give you this, but the formula on your formula chart is the energy for a single energy level. So I'm trying to do this using the formulas that you will have available to you. Then we're going, energy 2 would be minus 2.178 times 10 to the minus 18th. And we'll put that over our energy, or N squared, which is 4. In this case, 2 squared is 4. And if you cranked out that mathematics, we would get minus 2.445 times 10 to the minus 19th. Now it's energy, so that's in joules. And that comes from Planck's constant primarily on that. Now, your difference in energy, a delta, is always, with one exception that we'll see when we get to thermodynamics, is final minus initial. So we'll take 2 minus 5, and we get a minus 4.57. Let me not erase the whole thing again when I make these mistakes. A minus 4.57 times 10 to the minus 19th joules. So we've had two indicators that you need to wrap your mind around. High to low is emission, and if there is a release of energy. Negative means release in science. If there's a release of energy, that's also going to be an emission. So the answer to this question is, does it represent absorption or emission? The answer is emission. Now, the second part asked us to calculate the wavelength. I think we've got just enough time on this video to do that. So let's take a look. I'm going to leave that energy value there so we can use it. Now, remember when we move to a photon, that delta E is negative. We can't use a negative for the energy of the photon. Only take the value, absolute value when we're dealing with the energy of the photon. So our energy of the photon then is going to be positive 4.57 times 10 to the minus 19th joules. And we want to find the wavelength, so that would be equal to h. That's a constant given, 6.63 times 10 to the minus 34th, times c. I'm going to use 17 because I want to end up in nanometers over lambda. Now, I solved this for lambda. Here's my energy. Once I do that little bit of algebra there, I would solve for the wavelength, and I find out that the wavelength for that transition is not surprisingly 435. And the reason I say not surprisingly is because ending at n equals 2 is the Balmer series. That's what we saw in the visible range. You should have seen that in the video. And our visible goes from 400 nanometers to 700 nanometers. So you want to learn to start predicting a few things like that. Wow, that was a lot. That was on n. Now we're going to be moving on to the next quantum number. Until then, signing off.